electrical engineer, and is a partner of the graduate program here in University of Brasília. Then, please, Professor.
So thank you very much, Damasceno. Like Darli, I consider this university as my second home as well. It's an opportunity to see again friends, staff, and be here in this nice university. This subject of my talk today is a research outcome that reached the industry. Actually, it became a global standard in ITU-T, and more importantly, given that I'm here, it involved a student of the electrical engineering department of this university. Actually, a former student of mine that is now working towards her Ph.D. in Waterloo in Canada, Raissa. Before starting the technical content of my presentation, there are some highlights from my current university now. UFPE, stands for Universidade Federal de Pernambuco, is located in the vibrant city of Recife, that is on the Brazilian coast, in the northeast region of Brazil. So you can see here a Recife to Fernando Noronha crossing. It's like a competition of sailboats that happens every year. Centro de Informática is one of its schools. There are some universities that call institutes, faculties, schools. There we call center. And we have one of the top graduate programs in computer science in Brazil. I get to the outline of my presentation. So first I give a very brief introduction to time division multiplexed PONs with a focus on energy consumption. Then I mention the power management schemes for PONs, including those that were standardized by the ITU-T. For those that are not familiar with the acronym, ITU stands for International Telecommunications Union, and it is the United Nations specialized agency for ICTs, for information and communication technologies. And the ITU-T is the standardization sector of the ITU. So the main purpose of the ITU-T is to assemble experts around the world to develop global standards, basically. Then I talk about the Watchful Sleep mode, that is the power management technique we proposed that eventually became a global standard. I mentioned the ITU-T recommendations, and I finally conclude the presentation. So TDM PONs, time division multiplexed PONs, are a type of optical access networks. They use optical fiber in the distribution network. And typically a PON has a point-to-multipoint architecture, single fiber in a tree topology. So in the root of the tree, we have, in the root of the tree, we have an element called optical line terminal that is usually located in the central office of the operator. And in the customer premises, we have the optical network units. There are the boxes that are typically inside homes, buildings, or in the customer premise. There are two directions of traffic. The downstream traffic that comes from the OLT uses time division multiplexing. And in the upstream direction, the traffic that is generated in the ONUs that goes to the OLT uses a time division multiple access. And the OLT is considered the master of the PON because it transmits control, timing, management, and the payload. So the OLT is the element that connects the access network to the global internetwork. So energy consumption. So ICT technologies are responsible for a non-negligible, substantial percentage of the global energy consumption. Today, I prefer not to present exact numbers because the sources, they differ. Some say that the contribution is around 2%, 4%, 5%, so I prefer to use an adjective. And if we restrict if we restrict to the wired telecommunication networks, a great portion of the energy consumption is in the access segment. And this is not because the access nodes demand a lot of processing. The reason is that because they are numerous. So in principle, every home has an access box. And if we save a small amount of power or energy, and when it scales, we are saving a lot of energy. So let's make a very, very simple exercise. So consider an energy efficient light bulb that consumes, for instance, 20 watts. Typically this bulb is on 6 hours a day. And by the end of the day, it consumes 120 watt-hour of energy. And in the end of the month, 3.6 kilowatt-hour of energy. On the other hand, consider an optical network unit with several Ethernet ports that consumes, for example, 10 watts. So the power consumption of the ONU is less than the bulb, but it leads to a higher energy consumption because typically this box is not turned off. It stays on all day. So even though it consumes less power, it consumes more energy because it spends a lot of time on. And if we consider the price of the kilowatt hour in Brazil, for example, there in Recife, it approaches 70 centavos of real, and it's very expensive. Besides that, PONs are networks that have some peculiarities. So on the one hand, PONs, like any other telecommunication equipment, are subject to general concerns of power efficiency. But on the other hand, PONs should also adhere to strict requirements of sustainability and availability for critical lifeline services, typically voice. So if we have a telephone that is attached to a PON, it should be responsive when someone picks the phone to make a 911 call, for example. And unlike the electrical access networks, PONs are not powered from the local loop when there is a power outage. So PONs use batteries. So we have a trade-off here between the environment and critical services that we want to provide solutions. And what are the possible solutions? What has been done in this area? There have been some improvements in component design. For example, the use of VC cells, vertical cavity surface emitting lasers that consume less power. There are one-sided power management schemes specifically to the ONU or the OLT. For example, the power shedding is one mechanism that within this mechanism, the ONU turns off non-critical functions to save power. And there are protocol-based power management techniques that do require the exchange of signal information between the OLT and the ONU. So this work focuses on the third possible solution that is a protocol-based management scheme. The ITU-T, the standardization sector of the ITU, it standardized in the last decade two different schemes called cyclic sleep scheme, cyclic sleep mode, and doze mode. So in both modes, the ONU, that element that is located in the customer premises, The ONU alternates between an active phase and a power saving phase. And how it happens? Well, it happens through the exchange of signal information between them. So let's have a look on what happens in the power saving phase. So once in a power saving phase, the ONU alternates between two states. A full power state that is called the aware states. So the aware state where the ONU consumes full power, and a low power state. So the difference between the two modes, the doze mode and the cyclic sleep mode, lies in the semantic of this low power state here. In the doze mode, the ONU only turns off the receiver. Sorry, the transmitter. The receiver is always on. So here I have a graph that shows the power evolution here. And when the ONU turns off its transmitter, it still consumes, of course, it still consumes power, but it's a more conservative approach. So the ONU still listens to what the OLT is sending and only turns off the transmitter. In a more aggressive approach, that is in the cyclic sleep mode, the ONU turns off periodically not only the transmitter, but the receiver also. So these two modes, as I said, were standardized in the standardization process of them was finalized in 2010. So in order to implement, in order to enable these two modes, each ONU has to implement a state machine like this. So, and the OLT has to implement a state machine for every ONU like this. Of course, I will not get into the detail of this state machine, but for example, in this state, the ONU is a state where the ONU cannot enter a power saving phase. So we have transitions that may happen, for example, when a timer expires or when a local sleep indicator occurs. So given that, here we have 6 possible transitions, almost in identical ramification for the sleep and for the doze mode here. And these state machines, they are used to enable the doze and cyclic sleep modes. However, despite the fact that these modes were standardized in 2010, they have problems. And what are their problems? In the cyclic sleep mode, the ONU must periodically turn on both the receiver and the transmitter to probe for external wake-up stimulus. But is it really necessary to turn on the transmitter if the ONU only wants to receive external stimulus? Why not to turn on only the receiver? In the doze mode, the ONU maintains the receiver always on, even when there is no traffic for that ONU. As I showed, the state machines, they have almost identical ramifications for each mode. So the question is, why not to simplify them? And more important, the standard does not provide any technical reason for a separation of the two modes. So we came up with a new mode that is called the Watchful Sleep mode, and this mode was presented to the scientific community in a IEEE Communication Letters paper of 2014. And this mode, it unifies the two previously standardized modes in the ITU-T, and it combines their advantages. So instead of two modes, now we have only one single power management mode. And how does it function? So as before, the ONU alternates between two states, a full power state and a low power state. However, here in the low power state, instead of turning on both the transmitter and the receiver to listen to external stimuli, we only turn on the receiver for a very short period of time, and if there is no external stimuli to turn the ONU on, we go back to the lowest level in terms of power. So in this low power state, the transmitter is off, and the receiver, only the receiver, is periodically turned on to check for external indication. So let's make a very illustrative comparison of the cyclic sleep mode versus the watchful sleep. Here we have the power evolution. So as I had said, in the cyclic sleep mode, we have periods of sleep where the ONUs consumes very low power, but after the T sleep, I turn on both transmitter and receiver. However, in the watchful sleep mode, after T sleep, I only turn on the receiver. So this shaded area shows the saving in power consumption the watchful sleep mode presents when comparing to the cyclic sleep mode. When we compare the watchful sleep mode with the doze mode, as I had said, in doze mode is a more conservative power management scheme. The ONU only turns off the transmitter and maintains the receiver on. So here in the watchful sleep mode, we turn off both of them and periodically only turn on the receiver. So the shaded area once more shows the power, the saving in power consumption when we compare the watchful sleep mode with the doze mode. So in terms of state machines, instead of 6 states, now we have 4 states. We eliminated 2 states. So two states, the doze-aware and the sleep-aware, have been merged into a W-sleep-aware here. And the asleep and listen state have been merged into a state called the watch state. So we got to a point where we have now new power management mode that outperforms the 2 previously standardized modes, and it's simpler and it uses less signaling, because if we have a simpler state machine with less information exchange, we can say that less signaling is transmitted. And we built a performance evaluation tool to analyze the performance of these 3 modes. We built a discrete event simulator in OmNet++, that is an open source framework that uses C++ coding. And we implemented the 3 modes, the 2 previously standardized, cyclic sleep and doze, and the watchful sleep that there was initially called unified mode here. And we used traffic generators in both OLT and ONUs. So here we have a very, very general overview of the architecture. Sorry, of the architecture. Here we have traffic generators here also, and here we have a PON simulated using OmNet++. We chose a set of parameters based on a realistic scenario for an operator. One of our contributors belonging to an operator in the US. So the results I'm going to show are for this case 1. There is a scenario, a representative scenario for a power outage where all the functions of the ONU are disabled except the lifeline services. For example, that uses a 100 millisecond period for sleep. And when we compared the three modes, the leftmost graph shows the energy efficiency of the three modes: unified or watchful sleep mode, sleep, and doze. And with the watchful sleep mode, we obtained a very high energy efficiency compared to the two previously standardized modes. Of course, we lost a bit in the downstream delay because the watchful sleep mode spans a greater portion in the lowest power level. However, this increase in the downstream delay did not affect essential services like voice. And almost no increase in the upstream delay was observed because the T-sleep does not affect the local indicators. So given that these results were obtained and presented, the watchful sleep mode was presented in the ITU-T. So it was a long battle that lasted, I guess, more than 1.5 years with deep discussions. You can imagine that the standardization process is not a very easy one. There are many commercial interests. And fortunately, one of our contributors participated in the meetings. And with those results, he presented and defended the watchful sleep mode in the ITU-T. And in 2014, it was standardized by the ITU-T. So here I'm show one of the ITU-T recommendations that had been published before in 2010, and it was published again in 2014 with the watchful sleep mode as one of the power management schemes here. And more interestingly, the next generation PONs based on the TDM PONs, whose recommendation was published less than 2 years ago, in 2015. That are the 40 gigabit per second PONs. They have only the watchful sleep mode as the allowed power management mode. So we also showed that the watchful sleep mode can emulate the two previous modes as a special case. So the standardization guys, they saw no reason to maintain the two previously standardized modes for the next generation PONs. So the watchful sleep mode is today the only allowed power management mode in 40 gigabit per second PON systems. We also have two other publications, one in IEEE Communications Magazine, where we relaxed some restrictions in terms of the wake-up stimuli. And the bottom one, we presented the first analytical analysis for the watchful sleep mode in the literature. So I conclude my presentation saying that the separation of two power management modes reduces the power efficiency of PONs. And a system that supports the watchful sleep mode can emulate the two modes previously standardized. And we show that it outperforms the two previous modes in terms of energy efficiency. And the watchful sleep mode, that is as I said, it's a research outcome that involved one of the students of this department, is now a global standard, and it's the only allowed power management mode in next generation PONs. Acknowledgements, Denis Kotimski, that is the distinguished members of technical staff of Verizon Communications, that was one of our contributors, and this guy went to the meetings in Geneva several times in China, to defend the Watchful Sleep mode, and of course our supporters here in Brazil, CNPq, CAPES, and the State of Pernambuco State Foundation. Thank you very much.
Professor Divanilson, thanks for tonight's presentation. Now we have time for just one question.
Okay.
Please, pass to audience. Preference to Professor Darli.
I just would like to ask if you are aware already of implementations of the Watchful Sleep mode in products or not?
Actually, to be frank with you, I have not been following this, but since it's standard, and if there are vendors that sell equipment that on 40 gigabit per second PONs, since it's the only power management scheme allowed in this equipment, I presume that there are. But to be frank with you, I have not been following the implementations so far.
Thank you.
Thanks, Professor Darli. Thank you, Professor Divanilson. Again, we acknowledge